For number 6, we are interpreting the information given on this graph. So part A asks what is the concentration of PCl5 at equilibrium. Here we can see that 0.93 lines up with the concentration of PCl5. So at equilibrium, we know PCl5 has a concentration of 0.093. For part B, we're going to set up an ice table again because we're looking for the concentrations of PCl3 and Cl2 at equilibrium. We know we have an initial concentration of 0.16 per PCl5, that's given on the graph. We have 0 for both of our products. For the change, we're going to have minus x and plus x, since all of our coefficients are just 1. So at equilibrium, we know we have 0.16 minus x, x, and x. Now, they don't give us a Kc value, which is what we've been using to solve for x before. But what we do know, based on the graph, is that at equilibrium, the concentration of PCl5 is 0.093 molar. So we know 0.093 is going to be equal to 0.16 minus x. So we can go ahead and just solve for x through that information. We don't necessarily need the Kc value. And we get x equals 0.067 molar. So at equilibrium, we know the concentration of PCl3 and Cl2 is 0.067. For part C, we are basically drawing on the graph the change in concentration over time of these two species. Since they're the same, we're just going to keep them as the same line. And we're going to go, okay? So I just kind of estimated where 0.067 would be. And I know my initial concentration is, of course, 0, so I just made a curve showing that. For part D, we are actually solving for the Kc value. And we are going to use the values that we know for equilibrium to solve for that. So I'm going to erase my ice table here. So we know that our Kc equation is going to look like the concentration of PCl3 times the concentration of Cl2 divided by the concentration of PCl5 at equilibrium. We just solved for the equilibrium values, so we know we have 0.067 times 0.067 divided by 0.093. If we plug that into a calculator, we get 0.048 as our Kc value, and remember the Kc value has no units. Okay, for number 7, I'm going to find the Kc expression using the formula that is given, or the equation that is given, rather. So I have the concentration of our products, SO2, times the concentration of Cl2, divided by the concentration of SO2Cl2. For part B, I need to set up an ice table. Okay, so my initial concentration for SO2Cl2 is 0.543. Beginning, I have nothing there. We're going to have minus x and plus x. So I have 0.543 minus x, x, and x at equilibrium. Let's see. I am given the equilibrium concentration of SOCl2, so again, I don't have a value for this Kc, but what I can do is set up this expression, 0.543 minus x, is equal to the concentration of SO2Cl2 at equilibrium, which is 0.237. I can go ahead and solve for x, and I find x is equal to 0.306 molar. So that's going to be the concentrations of SO2 and Cl2 at equilibrium. For part C, I can plug in my equilibrium values to actually find the Kc value. So I'm just going to erase this and plug in numbers instead. So we have 0.306, 0.306, and 0.543. If you plug that into your calculator, you should, no, not 543, sorry, that was the starting concentration, my bad. 237. There we go. Okay, so if you plug this into your calculator, you should get an answer of 0.395 for Kc, which again has no units because it is a constant value. Okay, for number 8, we have the equation 2NH3 going to N2 and 3H2. Now I'm going to set up an ice table. So I use just S to recognize sample because we have a sample of NH3. We don't start with any here. Our change in this case is going to be minus 2x, plus x, and plus 3x. So at equilibrium, I'm going to have my sample minus 2x, plus x, and plus 3x. I know that my concentration at equilibrium of 3H2 is equal to 0.978. So I do 3x equals 0.978. If I solve for x, I find that 0.326 atmospheres is x. The pressure of N2 is equal to x, so that means that 0.326 is the pressure of N2 at equilibrium. Okay, so you don't necessarily need a value here of your sample to figure out what x equals either. And you don't necessarily need the Kc value. For number 9, we have the equation 4NH3 plus 5O2 yielding 4, I did that way too big, sorry. Scoosh that over. 4NH3 plus 5O2 yielding 4NO plus 6H2O. I'm again setting up an ice table. We don't know the original concentration, so I'm just going to put a question mark there. You can put literally anything there because it's algebra. We have 0 concentrations, so start for N2 and H2O are products. For the change, we're going to have minus 4x, minus 5x, plus 4x, and plus 6x. So at equilibrium, we have whatever we start with, minus 4x, whatever we start with, minus 5x, 4x, and 6x. Here I'm given that the partial pressure of oxygen is equal to 0.784 atmospheres. That's equal to 6x algebraically, based on my ice table. If I solve for x, I find that it equals 0.131 atmospheres. For NO, the pressure, it's going to be 4 times x. So if I multiply this by 4, I get 0.523 atmospheres for the pressure of NO at equilibrium. Okay, so those are all the problems worked out. Hopefully that helped. Let me know if you have any questions. Ice tables are very important. They probably won't go away. You just know, kind of got to know how to use them in different ways as we've gone through here. Okay, let me know if you have any questions. That is it.